Hey, how are you? This is a busy week. We have 3 seminars. Nice. Thank you. Thanks. It's a lot of work for you.
Sorry for being a lot of work.
It's okay, but I'm gonna try to need your help. Thursday, speaking of California Transportation Foundation, I've been assigned to talk about something I don't really do, but I know. And that is what has the current climate done to funding for academics and what has happened. So we obviously we have a lot of students. We're not. Yeah, see, it's been big loss, but I don't have to. Thursday,
I think we don't have data. I mean, it's not like somebody had done survey or anything, but
yeah,
yeah.
that's.
But I could give you another data point. We're required to provide like 1 year funding to admit the new PhD students because uncertainty of the federal funding of the whole, yeah. the
That's
whole-
perfect.
Yeah.
Okay. Yeah, I can only get, I know it's true,
Mhm.
but I have not tortured myself.
You
Yeah, you know, and on Thursday I'm gonna be in front of people. Yes, God forbid I ask you.
Yeah, I think pretty.
Yeah, I mean, yeah, yeah, but thank you for sharing that in your school. I mean, I think we can say.
Yeah, I mean, I really wanted to admit a student who's like excellent, but at this point, I don't have that much funding.
Right.
I mean, it's not like something that I know I will get like this. It has to be
I know.
already in the university,
Oh,
that kind of
Yeah.
requirement.
oh, you
It's
can't
like-
even go by faith.
Right, no, like I said, I have like a collaboration with a planning agency and they're gonna give us money, I mean, because
So
they're
it
not
can't
gonna
even be, it can't even be public, because nobody, there's no
no,
trust.
it has to be like
Because
something
there's
that's
no
already
trust.
in the
That's the
university.
chilling effect of trust, right?
They just want to be sure.
Yeah, thank you, that's.
I guess
What?
telling a story probably
Yeah.
as good as having data.
Yeah.
Yeah, you're
Yes.
joining us for that, right?
Yes,
Yes.
where are we going, have we decided? We're 10 degrees.
Yeah, maybe.
Doesn't matter to me, I figure we're going that way.
Yeah.
I'm gonna drive because I have to leave after, so I can. Normally we walk over there, but with the rain.
Yeah.
Yeah, so I can drive us if it's helpful.
Yes, I also think the news.
Yeah.
So let's get
Yeah.
ready for the.
Okay, and I'm gonna go shut my door.
Complete coverage.
That's what
Thanks for coming. We have 3 seminars this week.
Yeah. Back to back.
It's all pick the
Excellent
rainy
seminar.
week to come. I
Yeah.
don't know what.
All great seminars.
I don't know what
Yeah,
Just,
oh, yeah.
so it's an HDMI or?
It's a Zoom meeting, and join the Zoom meeting.
Oh, okay.
I don't know if you got my email, was last minute.
Yeah, I just think when I come to.
That's
the
okay.
conference,
Yeah, we'll cover.
Yeah, because I have a presentation tomorrow.
Oh, you have a presentation?
I mean, the.
Oh, yeah.
Yeah. So I'm gonna start with discussion part.
Yeah. Sure.
Actually, you know what, maybe if you just use your computer, oh,
Yeah. you
can I send it's a PDF file and,
Yeah, sure. Oh, you have a PDF. Oh.
Yeah.
A fresh one. He's on the
adapter.
Oh, it's already set up. Okay. Cool.
So when you think Jake's here, such having a lunch?
Yeah, he said he's coming for lunch, so it's, I don't know if he's joining us for the seminar.
That's the regular.
Yeah.
Oh. That's your,
Yeah, that's okay, that's stuff.
so I just put off it.
That's all right, I mean, maybe I'll talk to you. Okay, regarding this, talk to you.
Thanks, so grad student, prospective grad student.
You just project road.
Oh,
They just started. And he initially was on the sixth option, but now he said he can use.
yeah, I got it. Shot. I have this form, let me, give
Yeah,
me,
but then, we can talk to him.
yeah,
He looks you're aware of his situation or something?
don't know anything, I haven't talked to him in a long time.
Oh, okay, but you have his phone.
Doesn't he control?
Yes, I have his grad plan,
Oh, okay. Oh, great.
but I honestly thought he already graduated, so.
Okay. Yeah, so maybe but we need to get this resource to some spot.
Do you have
Because
like?
it's already.
Well, actually, I don't need it, it's right here, right?
Yeah.
I can just use my hand. But to change slides, I'll just go to the computer,
Or you
right?
can hold the mouse. You can hold the mouse and use the scroll,
Okay.
will that work, or? Interesting. Okay, yeah, now it's, now you can use the arrows.
Oh, okay.
I saw shot.
It should be here.
Yeah. Yeah, let's wait for a couple of
Sure,
minutes.
sure.
Do you want to have a coffee or?
Gotta get stuff to eat.
Fine, thank
Yeah, so let me introduce you. But you had Dean and the professor.
Nice to meet you.
Nice to meet you.
So.
You Massachusetts-Amherst?
Yes,
Yeah.
yeah. It's good. You're new?
Yeah, this is my third year here.
You're 30 years
Yeah.
old.
Coming all this way.
Yeah.
Appreciate it. Thanks for taking your talk.
Great, first time, you've never been to UCI.
You have the
I
ring.
know you, I know him for a long time.
Oh, should we call Jay or?
You're good, Brendan, right?
It's. Just to remind me who's here.
Good.
Instead, just leave. I would like to sign in.
Very good.
I'm just taking a picture for my sign-in sheet. You're officially signed in.
Nice.
That's what happens when the real experts are gone. You're stuck with.
You just what? Yeah. Yeah.
That water bottle. 3 steps over there. Too many creeks.
There's water right in the green bucket.
I'll get
Oh,
that.
I think it's water.
Thank you.
Mike, you didn't use the word.
I am very. Well, actually, cream doesn't have a ton of lactose, so.
There was a, no, next time I'm gonna get you the lactose for you.
I appreciate the berry mix.
Okay.
Yeah, good. Much better than the cantaloupe and
Me too. Yeah.
Okay, let's get started. Yeah, good morning, everyone, and thanks for coming. And it's a rainy day, and thanks for joining on the Zoom as well. And it's my pleasure to introduce my longtime friend, Professor Sam Gao from University of Massachusetts-Amherst. And Professor Gao is a faculty member in civil and environmental engineering, and her research focus is on travel behavior and transportation system analysis, with a focus on application in smart and shared mobility, and also transportation planning and sustainable transportation systems. And she is on the editorial board editor of Transportation Research for RP, and I'm also an editorial board member of the Part B. But I noticed that they lately upgraded to associate editor and change original associate editor to senior associate editor.
One.
I know there is a promotion, but it's a nice contribution to the community, and also a past associate editor of transportation science. And her research has been funded by various agencies, including National Science Foundation, FHWA, and RE. And Professor Gao is going to present her work on the joint estimation of a semi-Markov decision process model of related to vacant taxi matching. Please join me to welcome Professor Gao.
Thank you, Lennon, for the introduction, and I'm very glad to be able to visit UCI campus. Learn a lot of great things about your research and institution. So this is my first time at the campus. Yeah, and I told Lennon I brought with me our wet air when we had light.
It's
Almost
precious for us.
2 feet of snow. So my roof was having some challenge with that much of snow. So I bought that some of that here. Okay, so like Wenong has mentioned, I'm going to talk about some kind of behavior model. So to just put it in a simple way, how ride sourcing drivers like Uber or Lyft, how the drivers make their routing choices when they are looking for passengers, right? So that's the more extreme part, because when they have passenger on board, usually it's like kind of more or less some kind of trespass, right? So outline, well, as usual, I'll talk about the motivation methodologies, and we'll focus on case study in Shanghai, where we do have pretty detailed GPS data to give us ground truth, and some conclusion and discussions in the end. So I think we've already taken Uber and Lyft, and as passenger, when we arrive at destination, we get off. So, but have you ever wondered like where the driver will go next after they drop you off? Presumably, they would like to find the next passenger in the shortest amount of time. But then also, they want passenger to go to a place that's far enough that they earn good earning, right? So it's not a very straightforward question for them to figure out. And what drivers do is they have all kinds of strategies. I remember one time I was taking Uber to the airport, and at the end of the trip, I said, "Oh, I'm gonna actually stay in the airport because there are a lot of passengers waiting there." Then he told me, "No, I'm not gonna stay here. There's such a long queue at airport. It's better I just go to I know there's a area that's not far from the airport, and there's pretty good demand there." So drivers have different strategies. They're free agents, at least in the current business model. So the idea of this research is that I'm trying to use data to figure out like can we come up with a model to predict their choices of where to go next when they're looking for a passenger. And this can be an important component for a system level, let's say simulation model, if you want to evaluate some policies that could affect the ride hailing system. Then having a good behavior model of how drivers respond will be an important building block. So that's the main motivation. I just very interested in behaviors when we make decisions. Now, so what are the input and the models we are building here and output? So we have as input the spatial distributions of passenger demand. So that's so then we know where they are in a network. Spatial distribution of vacant vehicles, so basically the supply. So this model for the individual driver decision making. So it's like given that there's some kind of demand distribution, and given that there's also other taxis looking for passengers. So the distribution both demand and supply, and the observed trajectories of vacant and also for that matter, hired ride sourcing vehicles. So we do have the link by link trajectories, and the hired part, we don't use it, as I mentioned earlier. Once a taxi is hired, they just usually go to the destination of passenger using some kind of shift pass or some variation of that. Okay. So we are building actually two models. If you'll notice that in the title, I said like joint estimation. So the idea is that when the drivers are looking for passengers, their actions will matter, like leads them to other places, but also the underlying system dynamics of how the passengers and drivers are matched also play a role. So the two models we can include in this work is both the driver's routing decisions, and we modeled as infinite horizon semi-Markov decision process, which we're gonna talk about in more detail very shortly. The basic idea is that we treat this as a sequential decision problem. So we all know that Markov decision process is this framework for modeling sequential decisions. So you're at a location, you decide where to go, like where basically in this case, the next link to go. And once you arrive at the end of the next link, you continue another. So you do another decision of which link to take. So I basically treat this as a sequential decision making. So that fits nicely under the Markov decision process framework. So the semi part is really just saying that the transition time from one state to the next is not uniform. So for Markov decision process, that transition time is a single unit time. So, but when the travel time varies, and which is the case in a network where you actually account for the very different link length, and particularly, as you will see later, like we also treat the matched vehicles going to the destination as one single transition step, and that can be a very long time. So we have to account for that heterogeneous transition time. So therefore, we just need to trick this MDP to be a little more general. So so semi-Markov decision process is just a more general version of MDP. So that's the one, sort of the driver's model. Then there's also the system model, although it's a bit simplified. So the messenger driver matching model based on the demand and supply ratio, right? So that's the input that we have there. So we also want to estimate parameters for that underlying matching model. So the output will be the driver utility parameters. So in the decision process, we'll sort of construct a utility function that driver is trying to maximize, but it's parameterized. So the parameter will be our output, as well as the parameter of the matching model, which we will introduce very shortly. Okay. So we do the estimation jointly by using the trajectories.
Is one of the inputs also where the matches occur? When the matches occur?
Yeah, we know that, right? So the trajectory is a sequence of location
And occupancy level.
and occupancy level, whether it's vacant or not.
Okay.
Yeah. Feel free to interrupt me anytime. Yeah.
So do you consider ride sharing in this case?
No. So we'll start from the basic ones, and if it works, we move on to more complicated situations. Yeah. So we just assume that just one passenger per vehicle if it's hired. Okay. So for the Markov decision process, and we need to define like, state and action and state transition and so on and so forth. So we have a network with node set N and link set RA. So a vacant taxi's routing decision is a semi-Markov decision process, as is mentioned already. The state space as at this point is a pretty abstract, but action space, transition probability, all the standard stuff. What's new compared to a Markov decision process is that there's like holding time T, which can vary depending on the state and action that you take. We award R and also a discount rate per time unit. So it's a rate because we have a continuous time discounting. And yeah, so an SMDP is like an MDP at the time of transition, right? So we know that what's MDP is that your transition, your the next state only depends on the current state, right? The history does not matter. Now, SMDP is like that at time of transition is in terms of state transition probability. So only depends on your current state. But however, there is a holding time at the state before transition. So how long you stay in the previous state. So in the particular context, it's really just the travel time because we do this link level transition. And then the additional assumptions, the higher taxi is assumed to take a short path to the passenger destination, therefore its routing decisions are not part of the problem at all. So we simplify that as a super link going from where it's matched to the destination of the passenger. So what is in the state? The state is has two parts. So start with the part that pretty obvious is the node that taxi is located at. So node I from the set of the nodes, we call it observable because we can observe it from the trajectory. Actions at state I is the one outgoing link. So A, that's link ij from the forward star of node I. So as you can see, it's a pretty local choice, right? Link by link. Although like we do have, you will see later, it's a global objective. We're accounting for the total discounted return over the infinite horizons. Okay, so with the state and action defined, there is transition. So a vector taxi at node I take link A, which is also synonymous for action A. If it's not matched, then it just end up at the downstream node, sorry. But if it is matched, then to go from J to the destination of the passenger, let's call it L. Okay. And also this just show like, the transition time really can be so disparate. Sometimes just link time, actually travel time, sometimes it's the travel time of the whole high trip could be like, 10 minutes, 20 minutes, sometimes around an hour. Where link travel time is in a range of like minutes or even less than 1 minute. So, before we move on to SMDP, we said, okay, maybe we can just ignore the small difference between different link travel time, right? So yeah, when some link longer, some link shorter, maybe in the end, grand stream, not too big problem. Maybe it is, but then once you have this also the high travel time, which can range from like 10, 20 an hour, I feel uncomfortable just assuming that's the same as a short link that takes you only 30 seconds. So yeah, that's how I get to SMDP, which is not actually not much harder. Just but conceptually makes things I think just more principled. Okay, so that transition probability depends, of course, the matching property, as you can see, the two different cases. So I use P to denote the transition probability. As you can see here, it's also indexed by a theta, by parameter, we can consider that too. Yeah, so the probability of transition to state L, given you are at state I and you are taking action A, basically taking link A. So this is just a mathematical expression for the graph that I had earlier. Either you're not matched, so it's 1 minus matching probability, or you are matched, but then you sort of multiply with the destination choice probability. And at this stage, we are not having a elaborate destination choice probability. This is purely from observed frequency. So in that sense, it's a simplified destination choice model. So the focus here is really, get something right about the matching probability. So we come up with a model that says the matching probability, again, it's parameterized, depending on the ratio between demand and supply. So it's this next to exponential expression, but the determinant is, so the enumerator is basically pi is travel time, and alpha is the demand rate. So it's number of passengers per time unit and per area unit. So if you multiply with time, then you get this upper, well, the enumerator is the number of passenger arrivals per area unit. And what's in the denominator is the vacant taxi density. Remember, this is one of the input I introduced here. Again, this is the number of vacant taxi per area unit. Okay, once you do the ratio, that is units, multiply with the coefficient that kind of controls in a way. So what they're dealing with some so-called like matching with friction, this particular case, spatial friction. And so it's like even you have, so you imagine a case like if you have the same number of passengers and cars or vacant taxis in the same area, it's not guaranteed that you have 100% matching just because they could miss each other, so-called spatial friction. So we're just using parameter to control that kind of friction. And we're gonna calibrate this theta 2 from the data. Okay.
So, I mean, here the matching, this basically is matching probability.
Yeah, this is the probability. So the whole model is from the viewpoint of the vehicle. Vehicle is the agent. So for a random vehicle on that link, A, given that that's the demand and that's the vacant taxi density of everybody else, what is my chance of getting matched?
Okay.
And that's a number between 0 and 1.
Okay, so we're thinking about interdependent. I mean, how about other available vectors?
Yeah, so that's
captured.
Yeah. So this is not an equilibrium model. So we're not calculating that interaction. It's like from the viewpoint of a single agent, given that there is this background vacant taxis, there's other vehicles.
Okay.
What is the chance of me getting matched?
Okay,
Yeah.
so no like a feedback loop,
There's no
simultaneous decision competition. I was thinking like
No, it's not an equilibrium model. It's like, I mean, that can definitely be the next step. Once you have a reasonable behavior model and then you run it, say, okay, this is my decision, but then once I make this decision, when enough people make this decision, then the vacant taxi density will change.
Yeah.
And then my matching probability will change, that will affect my decisions. So there will be feedback. But this is like,
this is average.
Yeah, so assuming that I cannot control the environment, it's more like if you wish, you can view this as a short pass problem where the travel times are given, so but not in the traffic assignment stage yet.
Thank you. To explain,
how you assess the parameters and time to values, how to calibrate the values of that.
So we'll calibrate it, so because we observe the actual trajectory of the vehicles, including when it's matched, right? So like average length is matched. So that observation give you an indication of when you have enough such matching events, or actually even the sequence of links where they're not matched, that's also give you information, right? So you will be able to calibrate that theta too by maximizing the likelihood of getting matched here, not matched there. Yeah.
Okay.
Yeah. So it's part of the overall estimation. We're doing this jointly with the behavior model also, which I will talk about next. Now, so that's the sort of, if you wish, physics or system model of the system, like given demand and supply, what's the chance of me as individual vehicle will be matched at any state and action. Now, I also need to make a choice, right? So assuming more or less rational. So the idea is that the decision is made in a sort of so-called full state space that includes the observable location I that I mentioned earlier, just the node that you want to pick that, and also the unobservable epsilons. So this the random arrows. If you have taken discrete choice models, this is basically the same thing that you added to your utility function to make the utility random. The idea is that there are things that we as modeler do not fully observe, things that plays a role in the driver decision making, but we don't observe, so they get lumped into that epsilon. So the idea is, that is like driver actually knows that epsilon, right? So for example, it could be something that they actually consider, like some drivers simply don't like getting stuck in traffic. So maybe that could be the traffic condition. Of course, yes. I mean, we could also observe, but let's say in this desert, we don't have traffic conditions. So then that gets lumped into the epsilon, but the driver actually knows that. So that driver considers that traffic condition.
So you do not model any belief state for the unobservable part?
The observable part is just the location.
For the unobservable.
The observable?
Yeah, it is just considered inside the epsilon, no belief state modeling.
No
Belief state.
belief state.
Yeah.
So you mean the distribution of those?
Yeah.
Yeah, so we have to, in the end, if we want to write out the choice probability, we need to make some assumption about the epsilons. Yeah. So will come up very shortly. Yeah. So driver chooses a policy in the full state to maximize. So the color speaker is mapping from the state, the full state, mapping to an action. So to maximize the discounted, we turn over the infinite horizon. So K is the stage, because you could just keep doing this. I mean, of course, the infinite horizon is another approximation because they need to end at some point, right? Even though it's a stage probably with many stages. So if you each thing has stage over, say, like a 10 hours working hour, you might have hundreds of stages, but it's not, I mean, literally infinite horizon, but that's a modeling tool to make the problem more tractable. Yeah, so that once you have an infinite horizon problem, then the return need to be discounted. Otherwise, it goes to infinity in general, and then the problem is not well defined. This looks a little bit horrendous, but the whole idea is or summing over. So first of all, don't worry about that stuff. So we're just gonna say, okay, for given policy F, and will sum over the return over, well, sum over the reward over all stages. The stage is going from 0 to infinity, right? And this whole thing, epsilon here, sorry, the exponential, this is just discount factor because it's a continuous discounting. So with continuous discounting, you will, well, usually you have discount factors directly applied to your reward, but here it's just exponential negative. That's just typical formula. And the summation here is basically so at any stage, you need to sum over all the time that has lapsed from the beginning that I gave you the correct discounting duration. What's inside in the summation is just the reward that we can observe and the epsilon, the error pattern we cannot observe. Okay. So it's no different from any typical dynamic programming Markov decision process sort of object function summing over all the term. And the expectation, then we take expectation is parameterized with the theta2, the transition probability we talked about earlier. Okay. And then we assume they maximize this discounted total return. So that's, we have this up there. Okay. And that's defined as the sort of big V, the value function in the full space. Now, this is not easy to deal with when you have epsilon there. So don't worry about this one. The whole idea is that, okay, we can write some Bellman equation in the full space, and then we just take expectation of both sides of Bellman equations to get rid of that epsilon, because that looks very nice there. Of course, there's some assumptions that we have to make to sort of can get rid of the epsilon properly. So that's the detail that I'm gonna is not mentioned here. The whole idea is that if we do the expectation of the big V over the full space, so this is just the density function of the epsilons. We get this small v, and we also remember on the right hand side we have your Bellman, not here. I did not listen that, but in Bellman equation, the right hand side is always some kind of maximization. But since we need to take out the epsilon, so we have to have a function we call it social surplus function that involves taking first maximization over, some deterministic utility plus some random error, but then take expectation of that random error. So that gives us the so-called social surplus function. So if familiar with discrete choice model, when the epsilon is, let's say, Gumbel distributed, IID Gumbel, then the G is basically log sum. So you're basically saying, I have a set of random variables. Now, I'm first taking maximization and then take expectation. That gives me a log sum. That's a function of the deterministic part. Well, I mean, this notation we need so that we can work with just the Bellman equation in the reduced state space, in the observable state space. That says, the left-hand side is the utilities, so the value function at node I. Right-hand side, if you ignore the G for now, this part looks pretty familiar as a Bellman equation right-hand side, right? You have the reward of the current stage, and then you have your sort of like, cost goal or future reward, which is calculated by using the transition probability and your utility at your next state. But of course, it has to be discounted depending on which action you take, and sum over all the possible next state, right? So that's a typical Bellman equation. But since we're taking expectation from the full state space, the right-hand side actually involves getting this social surplus function. The maximization is sort of implicit in that G. Usually with Bellman equation, you have a maximization right here. Now it's become this G function implicitly including the maximization. Okay, so that I'm not sure that's too much detail that maybe, anyway, so the major theoretical result is that the mapping, because you have V on both sides, so it can be used as a fixed point mapping. The mapping is a contraction. So we have theoretical proof for that. I mean, it's not super complicated. We mainly use existing results, but because of our particular type of problem, we need to redo the proof from the beginning, even though it's kind of tedious, it's not. But yeah, that's technical details. So it's a contraction and there is a unique fixed point, small b. So that gives us reassurance that if you just simply do fixed point integration, it will converge. So why do we need this? Because when you calculate the the choice probability, like here in a specific example, when epsilon is identifiable, then the social surplus function is the log sum. So this looks, yeah, so the G now is basically the log and the sum of all the possible actions out of the current states. The choice probability then is your familiar logit model, the probability of choosing action A as state I, and it's parameterized by two sets of parameters. Theta 1 is a behavior parameter, so this is the utility function. So it could be like, travel, no, in this case, it's not travel time, more like, the revenue or the cost of choosing the action. And theta 2 is a parameter, as I mentioned earlier, the transition. And this is a familiar logit exponential of the utility of the action in question divided by the sum of all the exponential utilities of all the actions in the choice set. Now, what's interesting is that you have both the immediate reward and also the remaining your future, all the sort of like the future reward included. So this is where you use this small v, right? So that's why earlier we do all this work to make sure we have a way to calculate this g. Okay. So if you just simply ignore this second part, then that's not a sort of Markov decision process. It's not like you are taking into account your action, the effect of action on the future. So this is like, even though the decision are local, the objective is global. So yeah. Okay, so now we talk about the matching model, which affects the transition probability. We have the choice model. Once you essentially the epsilon 2 logit, you have that explicit expression of choice probability. Now, how do we estimate those theta 1, theta 2? We start with what we observe. We observe state transition tuples. So I is the current node, A is the link that this vehicle take next, L is the next state. So if I and L are connected, like basically the source and sink of the same link, that just means that vehicle is not matched, right? If L is actually far away, then or not physically connected, then that's destination of a passenger. Basically says at this point, once taking this node, the action A, the vehicle get matched and carrying the passenger to destination L. Yeah, so that's just sequence of those transition tuples. And we can process data to create many such transition tuples. And we can then write the the likelihood function of observing those transition tuples. Okay. So it has two parts. There's the parts that are related to behavior. So this choice behavior, and the second part is related to the transition. So the first part is only the first line here. That says, what is the probability of choosing the observed action, given that your current state is I, and with some, given parameter values towards the two. So this is basically the logit from the previous page. And then you have also the second part is the transition. So if it's not matched, means then you use the first part, right? So the probability of not matched. And if it's matched, then you have the second part in the local function. So basically, in one local function, you have both the behavioral likelihood and the system transition likelihood. And you have, of course, many such transition tuples to do the summation over all the logs. Okay. Yeah, I did not include a slide that says how we estimate this. I mean, we maximize the likelihood, but also it's computationally intensive because for any given trial value of theta 1, theta 2, you have to solve for the value function using the fixed point iteration I just mentioned earlier. So that's the main part of our implementation. But then once we have that, well, overall, we use the sort of BFGS algorithm that Python has a standard package for that. But it becomes more efficient if you can provide an expression for the gradient, right? So otherwise, Python will just use finite difference to calculate numerical gradient, which can be computationally intensive. So there's also some work that involved of calculating the gradient of the likelihood function. Again, that's also involves solving some fixed point problem, because if you take derivative of this with respect to theta, you'll end up also with requiring the expression for the derivative of the value function. And the value function does not have a closed form expression. It's just right. You have to do implicit gradient, and that involves solving another fixed form problem. But still, that will be faster than using the finite difference of BFGS. Okay, so yeah. So we do a case study in Shanghai, China, with an area. Well, it's a big city basically. Over 30,000 nodes and close to 30,000 links, now including centroids. And we are lucky to have GPS records of over 13,000 taxis. This is before ride-hailing becomes very popular. So these are mostly regular taxis at 10-second intervals. So at that frequency, we can feel comfortable of doing map matching and getting relatively accurate sort of link by link trajectories of the taxis. So we used just one working day back in 2015 in the morning for 6 hours. There's also the work involved processing this data is like map matching. You can hardly write about it, claim contribution, but it's just a lot of work, as students might be aware. And so my students spend a lot of time doing the map matching, but only 2 sentences in the paper. Yeah, so he used the open source framework. If any of you are interested in doing such work, and this is a good one. I know. Yeah, so it's a hidden Markov model to do map matching. The idea is that the actual ratings are not exactly on those links, right? So they're usually off. So what is the most likely set of trajectories that actually observed? So that so in the end, we have about 6 million transition tuples. We don't use all of them because it's gonna, yeah, very computationally intensive. But we have just a graph showing the study area. So it's a heat map of pickups in the 6 hours of a weekday, and not surprisingly, we see hopefully more pickups or higher density pickups in the city center. So those roads are like the ring roads around Shanghai, and we have major transmission hubs. You see, it's either airport or railway station. So there are a few railroad stations, one airport close to city center, and then A is the newer and bigger international Pudong Airport. That's a little bit out of place from the city center. Just some sort of observed data statistics. So it's histogram of occupancy rate. Occupancy is basically a number between 0 and 1. So the utilization ratio, like proportional time that's revenue generating. So of course, the higher the better. And there is a wide spread, and so the mean is around 0.5, about half the time that drivers are actually earning money. The other half are just cruising or searching for passenger. That is also spread. Some are really sort of either very experienced, good skill, or lucky because it's only 1 day data. Some are not so lucky. And just unit profit, that's distribution. So these two are related, but just different metrics. So the profit is basically calculated as the revenue minus cost. Of course, we have to make assumption about the cost structure and the fare structure. So just check the prevailing fare at that time and assuming some fuel cost. So the so the average profit, unit profit is about like 63 Chinese yuan per hour. So the first batch of results is regarding the computational time. So I'm not going into the details of each of these numbers here. The whole idea is I already mentioned earlier. So we have to do the fixed point iteration many times, basically for each trial value of theta 1, theta 2, you have to solve a fixed point problem. That's very intensive. So we try ways to speed up, including, as I mentioned this earlier, providing an expression for the gradient instead of relying on finite difference from BFGS, but also we use parallel computing. So Python has this easy way to implement that in Python is so if you do matrix operation, then it just automatically, not that automatic, but pretty straightforward. Instead of doing for loops, which never do that. And we also tried using GPU. It speeds up a little bit further than directly just using GPU, but not as much as we have hoped. I suppose that there's probably some further improvement can be done there, but that's not our focus. So yeah, some good answers here. Oh, and one thing, just using sparse matrix, save the memory requirement. Okay, now this is the actual estimation results. So as you can see that we have 4 models. The main model is our best model. The other 3 are sort of taking out some of the features. So the idea is to see like, how the performance could deteriorate if you miss one component or some other components. They all share the same utility function. So we have basically 4 explanatory variables, or in a more term in machine learning, like the features, if you wish. Anyway, the variables are used to explain the behavior. We have F is expected fair. Again, if you want to calculate expected fair, that means that you have to account for the fact that it could either be matched or not matched. So you have to have some kind of theta2 that's already specified. So that is we can estimate its theta2 separately earlier. Remember the likelihood function has 2 parts. We can estimate theta2 just by maximizing the second part of the likelihood function, and use that to calculate the attribute values or the expected variable values, the expected fair. We have also the expected operating cost. So just we assume some kind of fuel efficiency and just proportional to distance. We also have a link size. So that's something peculiar to root choice. So it reflects the overlapping between different alternatives. So you can view it as, overlapping between routes. I call it policy because it's, strictly speaking, it's a policy, it's not a single route, but similar concept. Because we use a Logger model. Logger, we already know that assumes the epsilons are independently distributed. But if the alternatives, the routes have overlapping, we can not say that they're independent. That's a classic problem in root choice. So there are various ways to handle that. So what we are doing here is we still maintain the loaded formula because it's easy to handle instead of the more complicated nested loaded or cross nested loaded or even. So we still maintain the loaded, but we just have some kind of correction for that overlapping. So basically we'll reduce the utility of depending on the level of overlapping between different alternatives. So that's a variable for that. We also have a LC, the so-called link account. That's just simply a binary variable 0, 1. So it represents the number of intersections. Okay, and also have an urban. Basically, it's whether we're in an urban area or not. So just the 4 explanatory variables. Then theta2 is the matching probability parameter we talked about earlier. Okay, so yeah, we report sample size, the initial likelihood, the final likelihood, because sample size is huge, so the likelihood is also a very huge number. What we are looking at is the adjusted rho square. That's our measure of model goodness of fit. So it's a number between 0 and 1. So the larger, the better, but also account for the number of parameters. So therefore, it penalizes a large number of parameters. But in this case, like all of them have the same parameters, so it's not very different from just simply rho squared. Anyway,
Can I have?
Yeah.
Oh, yeah. I have 2 questions. So, the fair I have here,
Mhm.
we understand the F as a equilibrium point between demand and supply, or the.
No, the fair is just let me see. I don't. So that's just we have the fair structure that says this flat fair for the first like half mile or so, and then after that it increases with the distance to certain slope, and then beyond certain distance the slope getting larger. It just so if you it's calculated based on a published fair structure, but it's expected in the sense that by taking a particular action, you could get matched or not matched, right? So if you are not matched, the fare is just zero. If you are matched, then there is probabilities of where this passenger goes. So that destination probability is from the data. So if you know the destination, you know the distance, that will give you the fare. Yeah, and you take expansion over all the possible destinations, give you expected fare. Yeah.
Yeah. I have one more question.
Sure.
Yeah, because I'm also doing t-test right for my ministry,
Mhm.
and I'm considering if I have to check all the assumptions under the t-test. So I wonder how have you checked the kind of assumptions under the t-test or not, or calculating t-statistics over there?
Yeah, so we also do t-stats, so that's why we report it. So this is how we decide whether the parameters are significant or not.
Yeah. So for the t-test, we have some assumptions, right? So
Sorry, some
assumptions.
Assumptions,
Yeah,
yes.
assumptions for conducting t-test.
Mhm.
So I wonder if I have to check all the assumptions under the t-test or not.
Mhm.
So I would like to ask that how kind of did you check for the assumptions for the t-test here?
Oh, you mean like whether the distribution of the outcome is really normal or
Yeah, this kind of.
that kind no, I mean, we did not specifically check that, but I think with large enough sample, like the arrows generally are normal distributed. And also it's not simple t-stats. We calculate again, this is done not through a typical like off-the-shelf software. We have to calculate our variance covariance matrix ourselves. So we use a so-called robust t-stat, so to account for the fact that your model actually is not true model. So t-test works when you are working with a true model, but you never know whether my model is true or not. So there are ways to correct for that, and the so-called robust t-test. And so we also account for that. So the so-called like sandwich estimator of the variance covariance matrix. That's our way of doing that. But actually, doing sort of this checking, no, I didn't do that. Yeah.
So I have one question for the fare structure. I remember it not only depend on distance, also time, right? If there's a heavy congestion, there will be extra charge for some congestion related.
Right. We checked the published fare structure during that time, like 2015 in Shanghai, and that's just a distance-based fare structure. That's what we used.
Okay.
Yeah.
So no extra charge if they got stuck in the traffic. I remember maybe different city.
Maybe.
Yeah.
Yeah.
Okay. So maybe that's also kind of related. I mean the expected operating cost could potentially depend on the congestion level as well.
Sure.
But such that it's urban, this binary variable is used to take into account the congestion effect or no? Or how do you define urban or what is the impact? It looks as significant, right?
So this actually is the urban is multiplied to the variable called link count.
Yeah.
So that's basically representing number of intersections.
So
the intersection. So if you have that interactive term here, it just says that the number of intersections has a play a role. It's negative, so just basically says drivers don't like going through intersections, but only in the urban area. So in the once outside urban area, that parameter is not significant.
So urban
we did
area,
estimate both, but we dropped the insignificant ones.
Maybe more waiting time at intersection.
Probably,
That's might be related.
Yeah.
To that. Okay. That seems to be pretty significant in terms of the T value, T stat.
Right. So this urban is just to regulate the effect of the number of intersections. Yeah. So we're saying it significantly in urban area, but not in the suburban area. Yeah.
Did you cover the different columns, single cycle, IDR, sequential, and main? What the differences are?
Oh, I have not.
Okay.
I'm just so here explaining the features, the variables. Yeah, so observations, so all the parameters are significant. I mean, that's not a very useful statement in the sense that if they're not, I already removed them anyway. But they're highly significant, except that of the link size, which I'll explain later. So the size are also expected. So you have positive for fare and negative for cost and number of intersections. So the interesting part is that, we decided at early, the first version, we lump the revenue and cost together as business profit, right? So naturally we think, we want to maximize profit. But then when you're talking about human behavior, humans are not rational. Well, I wouldn't say they're not rational. They're bounded by other constraints. So it's okay, let's just separate them. So it turns out, if you look at the numerically, they're different, right? But also statistically, we did perform the statistical test of the absolute value of these two, and they're also different. So specifically, it seems that drivers value the fare more than the magnitude of the fare, more than the cost. Of course, one is positive, one is negative. The idea, one possible reason is that maybe because the fare is displayed and shown to you, to the driver every time that you complete a trip. So it's right there, it gets your attention. It's like the gas price. They really ostensibly right there. I mean, it's like you have to pay attention to that. But the cost is not like a per trip basis. It's not with maybe your ownership cost, your maintenance cost. It's really hard for you to discern it. So that's my interpretation that why the cost actually is, the sensitivity to cost is smaller than.
It's also your cost model, right? Like you decided the cost as opposed to collecting the revenue data from the real world, right? Like, do you have ground truth information on the costs?
The cost. So again, we calculated,
Right.
but based on we try our best to make it as true as possible. So it is based on some fuel efficiency and the actual distance that they traveled. So
Yeah, no, I'm just saying, like, you could have got it wrong, right? Slightly. You could have calculated depreciation slightly differently.
Yeah,
than
right,
transit. I
right.
think the more
That's
likely,
true. Yeah.
the more likely reason is exactly what you said, is that their own mental model of the cost is probably undersells the cost associated with actually operating a vehicle. I mean, we found that with Uber and Lyft drivers, like they're not taking into account depreciation at all when they're making decisions, right?
It's hard when long-term thinking is it's always hard. Right, you're right. So I think, so this cost is only operating cost. And if I don't know, even just with operating costs still.
It's an interesting finding, even if you can't perfectly explain why it happened, right?
Yeah, we can only say some plausible explanation is that okay. Right, so that's the link size. That's an interesting variable, as I just mentioned. It's actually has two rows here. The one that I already explained earlier is that we're trying to correct for overlapping, right? So we assume a logic model, but the routes are actually overlapping a lot of times. So we reduce the utility by the extent of overlapping. Basically, we penalize overlapping. But then that's from the modeling, sort of just more technicality of the logic model. But behaviorally, people might like overlapping. So this is another thing I discovered over time, like, when I work with commuter route choice, is that if you can take a route that overlap with many others in the sense that they have flexibility to detour if something happens on your original route. So overlapping gives you the sort of the option value. So that's a positive thing. And probably in this case, these two opposite forces somehow cancel out, and it's a pretty small, both numerically and also not statistically significant. Yeah. So
Can I ask a question on that?
yeah,
one? So if the choice is just the a downstream link,
right.
like what is there's no overlap, right? It's like either you choose a link or you choose a different link. It's not the same as a path, right? Where the links could overlap.
Right, but
Distinct, right?
yeah. So the immediate next link do not, but when we calculate the
cost to go.
the cost to go, we include that small v, and that's calculated through all the possible future extensions of your route.
A little hard to think through as well.
It is. It's not like a straightforward traditional. You have just one choice set. You make a choice once. This is how you have sequential. So this the cost to go or the return to go, whatever, includes the
Okay.
So I feel in this situation, maybe because it is kind of independent because the destination choices of are determined by passengers, not really if they are matched, not really by the driver themselves.
no.
So then, I mean, I don't see even if like passenger A goes to this place, passenger B goes to the place, even though their routes overlap, I do not see interdependence here at all in terms of
Oh,
choice.
so this is about like if you have a choice set,
Mhm.
like this is a choice set. It's basically all the possible route you can take,
Um,
and they're definitely gonna be overlapping, right?
I thought this related to the L, right? The given I, you want to choose a destination. No,
So no, this is not choosing destination. Well,
No.
it's choosing a next link.
Mhm.
Once you are at the end of next link, you will choose the next link again. It's not a direct destination choice. But even if it's a destination choice, you can still have many alternative routes to go to that destination,
right.
and many of them could be overlapping.
Right, but I see this overlapping. I might be. Well, I mean, this overlapping does not really violate IIA in any sense. I might be wrong because these are related to choices for many different, basically passengers. If so.
No, this is for the. So first of all, we're talking about the vacant taxi. So they need to want.
Yeah, vacant. Yeah. That's,
so there's no set destination that can be observed. Actually, that's one issue. Not one challenge associated with vacant taxi model is that there's no destination observed. We observe when the vehicle pick up a passenger, but we cannot just say that's the destination because it could be that I could be aiming towards the city center, but on the way to that, on the outskirts, actually I get matched with a passenger. So it's not like I'm actually going to the outskirts. That's not my destination. So therefore, we use the sequential decisions, like where your next state is depending both on your choice and also the underlying matching process. So that's that. But your question regarding whether they're overlapping, the thing is like you can view, even though the choice at locally is only a next thing. You look at it globally, it's you're choosing a policy that maximizes your expected total return over the infinite horizon. You're actually summing over all the possible future state. So there will be a lot of overlapping. Like, for example, if you only two steps, it could be a policy that says the first step is the same, take turn left, but then the next intersection, one will turn right, or one will turn left. So these two policies will actually share the first part of the route.
Yeah, but did you say, I mean, traditional, because in traditional, stochastic network loading or stochastic route choice, definitely the overlapping seems to be significant.
Oh, yeah.
Did you, in a traditional setting, did you see the significance of,
Oh, yeah.
overlapping? But
Overlapping.
here it's not significant, right? If I understand correctly.
Right, yeah.
So this discrepancy, so that's very interesting.
So even in the commuter choice, we also have, I did not do, but so Emma Freshinger, who is a professor at University of Montreal, worked on the route choice, just regular travelers for quite a while. And her work in Part B, like probably 2016 or something, has even earlier than that, sorry. Yeah. I'm getting confused about the decades. Should be 2006, not 16.
Was probably.
It must be 6, not 16.
2006.
I mean, a range.
20 years ago.
Yeah. So she estimated this same type of correction. That's a traditional path choice problem, so it's for the path size. In that case, usually the path size should be well, I mean, it's the opposite of this. That means it's like, usually it should be a positive sign because the path size is, the variable itself is smaller when you have more overlapping. Anyway, doesn't really matter. What the point is that she found the opposite sign, according to sort of the fact, if you're just purely correcting overlapping, then the sign should be positive, but she actually found negative sign, the opposite. And it's very robust across all kinds of models she tested. So at that time we discussed and we said maybe there is people actually value flexibility, and that's why. So this one variable carries 2 rows, and so in her case, it's actually moved to the other direction. The sign country flipped from theoretically, yeah.
How about significance? If it's a
significant.
But here is not.
No.
Yeah, right. So that is
yeah. Right.
That's interesting.
The significance is not about the existence of overlap, right? It's just about the impact of it on the choice outcomes.
Right.
So it has 2 opposite.
Basically, I take it as whether the violation of IIA is significant. My interpretation might be wrong, but I'm taking.
Oh no, it's not.
It's not.
No. It's what whether this particular variable that captures overlapping affects behavior.
Right, but the overlapping, whenever we have a stochastic route choice, when there's overlapping, basically 2 routes violates the IIA condition, right?
Yeah, that's almost given that you have to correct for it one way or another.
Right.
Yeah.
But if the correction is not significant.
But it's because it also carries some other behavioral interpretation that people actually also like overlapping.
Like overlap.
Yeah.
Okay.
So the correction for that's purely the modeling mechanism is that, okay, if I don't want to do this correction, I need to use maybe nested loaded or cross nested loaded that explicitly account for the correlation between the epsilons, and the model becomes a little bit ugly, hard to handle. So I want to still just use loaded, but then I'll just correct the deterministic utility by introducing this overlapping variable. Yeah. So that's just sort of, if you wish, a shortcut, not using the more complicated model. But so in that sense, it has no behavior interpretation. It's really just, I don't want to use loaded. I'll just use loaded, but then I need to correct for the overlapping.
Okay.
And then I say now it might have actually some behavioral interpretation, like people actually like having that flexibility that in case something happens, you can go to a different route. Yeah.
Okay. Yeah.
So it seems that in this case, this cancels out. Like in Emma's case, it actually goes the other direction. Yeah. So I guess the point is that when we look at the correction, the past has links as we should not simply just assume its theoretical value, because you could just not estimate the parameter. You can set it just to be the theoretical value from the theory that underlies. Okay, let's see. Yeah, so then this is we have three sort of if you wish baseline, but it's more like I have the full model. Now I'm changing some of the components of the full model and see how the estimation goes. So single cycle, actually this is motivated by a model in the literature. So the idea is that I still do MDP, but I stop the process once the vehicle is matched with a passenger. So I don't care where the passenger goes. I don't care what the driver will do after dropping off the next passenger. So just one single cycle. So it's like assuming drivers are not that much forward looking, right? So MDP is the process of saying, decision maker can be forward looking. I'm not looking at right now, but also in the future. So single cycle is sort of like saying they're probably more myopic or short-sighted. So that's the first base model, and it looks like the model fit has suffered a little bit. Maybe an indication that drivers can look beyond one cycle. So there's also the second baseline is sort of high discount rate. And high discount rate basically means that the future is discounted very significantly. So it's saying I'm still looking fully forward. It's still fully infinite horizon, but discount rate is very high, so that the future almost still doesn't matter. Yeah, so the model fit is still suffers a little bit better than the single cycle, but not much better. Then the sequential estimation. Okay, so I did not talk about actually this theta 2 here. This is the matching probability parameter. So you can estimate the theta 2 just by maximizing the matching probability part of the local likelihood function. And then you treat that theta 2 as given, and then estimate the other 4 parameters, behavior models. I call it theta 1 earlier, and just 2 sequential separate process. Or you can just estimate them all together by maximizing the overall likelihood simultaneously. So again, it seems that joint estimation is better, and that's not surprising. I mean, it's actually pretty standard intuitive results. Like joint estimation usually is better than sequential one because you make use of all the information more efficient way instead of treating some part of as fixed and just estimate the other. So joint optimization is better than optimizing them separately. Yeah. Okay. So, and here just visualization of the estimated, or if you basically that means it's the choice probability of the moving direction from the estimated model. This is not observed, this is the estimated. And we plot it in a way that's, you have the 8 directions that it can move. Obviously, it has to go through some aggregation because the choice model we have is at link level, and links can go all kinds of directions. So just there's some aggregation we do. Yeah, so going north, northwest, northeast, west, south, and so on and so forth. So the more like some green or yellowish color, light green and light yellow means that they're more or less sort of uniform or more random, and extreme values either is 0 or 1, like very sort of the darker values means that their choices are more extreme. So closer to 0 or 1, the lighter values like in the middle. So we can see that basically in the city center area with light green and yellow, the movements are more random, which is probably because we have high demand, going either directions will probably won't be too bad, equally attractive, but in the suburban areas that movement is more intentional, directional to probably high demand areas.
So this is a whole day.
This is 6 hours, so 5:30 to 11:30. Yeah.
The directional probabilities, so should they add up to 1 for every cell? No.
Yeah,
They should.
they should.
Seeing too many reds than I would have expected.
But they probably,
There
don't
are
get-
predominant directions, right,
Yeah.
for each of those cells, which are pretty much, most of them go this way, and nobody in other directions. Well, maybe the street layout is.
yeah, that also comes
is
play.
causing, okay, makes
Yeah,
sense, makes
yeah.
sense.
Okay, and there's also a comparison with a zone-based MDP model. So it's actually something that I've been wanting to do a while, and the motivation for the link-based SMDP is that I think it's a natural structure of our network. I feel a little bit uneasy, like we see everybody's doing this hexagon, it's arbitrary. They're uniform, so you assume that the travel time or the transition time from one hexagon to the next is the same. So you can use MDP, you don't have to deal with the mess of SMDP. But I always have suspicion that that kind of hexagon structure somehow ignore the underlying network topology. And if we can do the network with sort of with the true network, why not? So I do also the comparison with zone-based MDP, but we have to process the data because these two models are based on same data sets. One is the link level, the other is zone level. We cannot, for example, compare the model fit directly. It has to be that in the prediction test. So we have divided this into two parts. There's estimation set, there's the test set. So the comparison is purely based on test set. But even on the test set, we still have to process the output in a way so that the prediction from the two models are the same resolution, right? Because the link model will predict link movement, the zone model will predict zone movement. I mean, they're not directly comparable. So we have ways, we think we have come up with some reasonable ways to convert one to the other, right? So from zone level to link level, if the decision is to stay in the zone, so we just assume this person will do random walk within that zone. If the decision is to move to a neighboring zone, then they will take the short path from the centroids to centroids, right? And once they arrive at destination, they'll do random walk. Now from link level to zone level movement is a little bit easier, right? So you have the more granular movement, you just do aggregation, see where it ends up with at the end of each. You also have to specify a certain time period to even determine what your zone movement is. So here we use 4 minutes interval. So it's, from the observed data, the link level movement is straightforward. It's right there, link by link. But what is actually the observed zone movement, that part is not even clear. You have to specify a time interval, say 4 minutes. If at the end of 4 minutes, I'm still at the same zone, then I assume the action is stay. If at the end of 4 minutes, I'm at one of the neighboring zone, then the observed action is moving to one of the neighboring zone. So yeah, so going from link-based to zone-based in terms of the output has to go through the same process, right? So that's that. So we have basically for the link observation, not surprisingly, link-based model would do better in prediction. And the difference is significant. Here, not statistically significant, just numerically quite different. Link-based model 0.3 something, and if you use the zone-based to make prediction, half of the fit. Now, if we do the prediction test on the zone observations, the zone-based model is better, not surprising, because it's asked to make prediction at the same level that it's estimated on. But the link-based model is still okay. I mean, in terms of the deterioration, it's not as much as the deterioration of the performance in the other direction. So what I conclude from this is that I think once you do the more granular model, I feel that captures the network structure, your model is more robust when you're asked the model to predict movements at a different level that is estimated on. That's my takeaway from that. Okay, yeah, so I'll just go very quickly. I mean, sort of more like ready to work what others have done. You know, it's a long history. Earlier for taxi movement behavior, you started with as part of the traffic model, but without empirical calibration. I can assume there is a such model, and we're interested more like in equilibrium theories and properties, so on and so forth. Later on, there's more like empirical studies. Empirical means that given observation, trying to figure out the model parameters. So, like I said, the destination is actually not directly observed. It's so people make sometimes assumptions saying, okay, I only look at airport trips. Okay, so then that's very obvious. Airport is the destination. And some people do, some study do assume that just the next pickup and have observation about using that as the true destination. There's also a work from 2015, researchers from Hong Kong. They're doing like independent but still sequential labeling zonal choices, very much like what we do here using Markov decision process, but there's not a principled way to connect your local decision to a global objective. So it's more ad hoc. But then later on, I think we sort of more or less converge to using this MDP. It just seems a very natural framework for modeling the choices in a sequential way. Yeah, this model-based approach means that there's some kind of underlying model about how the system evolves, even though it can be very simple. I think in Eureta's work, they just use the observed matching frequency as the matching probability. There's also model-free approaches, mostly from researchers in computer science, that they just not deal with the transition model at all. But there are ways to, sort of still estimate the behavior model with that. And very interesting approach. I might explore a bit more in the future, see whether I can also use some there. Because making assumption about the physics of the system itself can introduce modeling bias. So if you have a large enough data set, maybe it's directly estimating the behavior model without worrying about system. If there's a way to do that, why not? Okay, and the matching function, again, it's not focused on this one. I mean, as you can see, I use it's a reduced form, meaning that I don't argue that an underlying process of how they get matched. So the matching function actually also comes from the econometrics literature, like, in the labor market, right? Employers and workers are trying to find jobs. So there's also friction. It's not like if you have enough employer, you have eligible workers and everybody can get matched. So that friction. So it's adapted to the taxi market early on. Now you can have sort of mechanistic model that builds on detailed matching process, like queuing theories, or reduced form that use a forceful function form, such as Douglas. Yeah, but typically, at least I haven't seen any short estimation of both matching function and behavior models. Yeah, seems to me it's an easy extension, but somehow I haven't done it. Yeah, so to conclude, the SMDP framework is, at least in this case, adequate in accounting for the varying holding time in a sequential decision-making process. The case study in a large network demonstrates the computational feasibility. So, I mean, the estimation still takes like 5 or 6 hours, but it's doable. No, we're not doing like real-time estimation or anything, so. The expected operating cost, the number of intersections in that area are found to be significant predictors. And interestingly, drivers perceive the fare and cost in a different manner. And we see that there's an advantage of considering multiple decision cycles, low discount rate, and joint estimation of routing and matching parameters. So the low discount rate, again, put it in a more behavioral interpretation, is that drivers seem to be able to look forward or look ahead instead of just being a myopic and just immediate return. Yeah, and also the link-based SMDP seem to be more robust than the zone-based MDP when they're asked to predict at a different level that they're estimated on. Okay, I think I'm over time. So these are not like four.
That's okay. Yeah, we have time.
I just want to say, like, this is not directly related, but the recursive, or it's called recursive loaded, when we the type of choice model I just described, but it's more generally called like dynamic discrete choice model, started from early work by Rust, his economist. Very general theoretical development, but then later on, in 2013, Foster and Emma Freshinger adapted to rechoice in a static and deterministic network. So their motivation at the time is really just to avoid the issue of generating choice set, right? So we all know root choice modeling generating choice set is a big headache. And a lot of the choice generation algorithms are just pretty heuristic and not really able to come up with forms. So yeah, this will avoid the issue of choice generation. There's some, of course, later extension, like stochastic time-dependent network. And this current work is another way of making use of that framework. And also including not just the behavior part, also the system model estimated together. Okay, so yeah, and then I look at the models. Okay, things that I know that I should have done better, but I don't have time to do it because I need to get the paper submitted. What if, first of all, okay, maybe this is not really, this is more fundamental. What if I don't have the high frequency directed data? So the data have 10-second interval, usually not available. I got it from China. and through some connections. But generally, we don't have that. Most of the publicly available data in the US are just pickups and drop-offs. But we could, based on the same modeling framework, instead of writing the probability of observing the next link, I can calculate the probability of observing my pickup location given my previous drop-off location. So of course, it's not as good as the actual trajectory it takes, but still, it can be done. So that's what we're working right now. So partially observed MTP with just pickup and drop-off. So I believe that's going to be much more helpful with the data set we have, and generally available for public. Then there's also like use one single set of parameters enough for heterogeneous population of drivers. As you can see earlier, it's a very widespread of income. So no, probably not, but start somewhere. So we could, work with latent driver classes. So this can be like some predefined driver classes, like, by going through the data, it might be different type of, strategies. Some always go to high demand area, others always sort of just stay where they are. And they could even also have different parameters. Now they have the same set of parameters, right? So that's just very typical of any distribution model once you want to account for heterogeneity. So I think that can be done easily the same way. That's not a heavy lift. Yeah. And this is a more challenging one. I don't actually know exactly how to do it. I just have an idea. So are we concerned about using the observed pickups as demand, right? So I got that question every time I say something like, and that's also something I ask myself. So my students always ask me, oh, is that? So it's okay, for now, let's just do that. But if we want to actually have a demand model, we need to add that to the picture. So the model we have right now, you can really view it as a supply side, right? So the suppliers are the drivers, and given some kind of demand, they make the decisions. There's also the demand, the passenger, how passenger decide to stay or leave. So then you have simultaneous supply demand equations. Either you treat, so then the host of other issues that we have to deal with.
And then you just use the lambda in the numerator as the observed pickups was in your.
That's what we do right now.
Okay.
Yeah. That's gonna be introduced in quite some way.
Sure.
Yeah. And then of course, like how the model be useful, like big picture, you can be part of just some simulator or you put in a model. You can just use the high performance drivers strategies, just can be used directly optimization problem solutions. Like, now I also work on Western problems. So I sometimes some optimization problem, maximizing is some optimal subject to some constraints, but you can just mimic the experts, right? It can also be a basis for drivers' decision support system. The idea is that if you want to help driver make better decisions, it's good to know like what the baseline is instead of just directly saying, okay, do this, do that, right? We all know that, we learn better when it's some kind of related to our current learning path. Yeah, okay, so that's all I have. Thank you so much.
We have any more questions? Great discussions, great presentation. Any more questions?
Any chance you could get ride hailing data and work with this modeling framework? Right. So 2 questions. Can you give a way to get the data at this resolution, and how do you think you would kind of revise the modeling framework in a ride hailing or a TNC type situation?
So if you do have the same level of granularity for ride hailing, I don't think the basic model will be the same. I don't see any fundamental difference. You might want to tweak your matching model because street hailing might have different structure than, this ride hailing, they can be matched with someone a little bit far away. But I think that's saying you are having a different matching model, but the whole framework could be the same. I don't. Yeah, but if you don't have, okay, sorry.
No, I have like kind of two hypotheses. I'm wondering if we could check with parameters in your model. The first one is that drivers are smarter than the shortest paths that are given to them.
Oh, yeah.
Right, in the sense that like if they know there's two paths, right, and one is closer to where demand is presumably going to arise, they're much likely to go along that path than they would the one that's not near the population centers if they're looking for that additional ride, right, that additional service. And then the other one is about this hexagons versus link-based routing. So a lot of researchers, and including at Didi, use reinforcement learning built on Markov decision process models around the hexagons. And people have heard me say this before. I suspect that they don't use the hexagons, these companies.
Oh.
Well, Uber has told me they don't. That they actually do make kind of deterministic optimization with a bunch of extra terms in their objective function to do the matching problem. But for repositioning, they do use the hexagons. And Didi's unclear about what they do. They have a paper from like 2017 or something saying they do use reinforcement learning for the matching on hexagons. And I'm pretty skeptical that that's what they actually do. So I think there would be.
Oh, you're saying even though they say on the published paper it's a based hexagon, but they don't actually do it because okay.
That's also what the guy from Uber told me, is that like he thinks it might have been corporate misinformation.
Oh.
Because they tested it at Uber and it just didn't work.
I see.
Yeah. So I think if you had the data, I think we could run it through your model, figure out the right parameterization of the model, and then look at the t-scores to see whether or not my hypotheses hold up or not.
Ooh. We are taking it really far. Right?
I'm not going to do it. So I mean,
disprove papers out there, or show that they must be wrong in the paper.
They have an easy comeback and like your model is oversimplified, and we don't lie. Anyway, so it'd be interesting to see what it looks like with the ride hailing, because it is different, as you said. It's not street hailing.
Yeah.
So the choices they're making, routing in the city, is a little bit different.
I'm not sure how to get. I mean, unless you have collaborators from those writing companies, right?
We'd be like, hey, Didi, can we have your data to prove that you're lying?
Yeah.
Do you have any conceptual idea to distinguish between the demand versus observed pickup? Conceptual idea how to distinguish between the demand, willingness demand, or within this time, or versus observed pickup? Like
so yeah, this is a very rough idea that I probably had on the way driving here this morning. So you have to have a separate demand model that says maybe the demand is a function of waiting time, right? So waiting time, waiting time in a way can be treated as a price in a typical consumer market, right? So in a consumer market, like how much a supplier decide to produce depends on the price, like basically how much they can make money. So in this case, the driver, but how many the demand also depends on price, right? So how many gallons of milk I decide to buy depends on the price of the product. So here, I think we need something similar. Maybe that price variable is waiting time, or some generalization of that affects both demand and supply. And you need to then write out your simultaneous equations, like on one side, demand is a function of the price. On the other side, like the supply was one of the price, and they're also interacting. So there's very classic econometric techniques to model the so-called simultaneous equations when you have both demand and supply and interacting. And there are econometric issues that you have to deal with, that your estimates If you don't do any treatment, they'll be biased, because it significantly violates some of the assumptions. Yeah, that's about it.
That's like a market,
I'm not even sure they can work.
it's like a market clearing waiting time somehow, right?
Yeah.
What about like, I mean, maybe working around it, it's like trying to figure out the probability of misdemand, like, or unserved demand, which would also relate to the supply demand dynamics, right? If there's no vehicles there in a particular area,
Mhm.
the demand can't be realized,
Right.
right? So, and you know where those vehicles are, you know where the demand is realized, but you don't know where the demand is not realized.
So we definitely need more data to figure out, right? So it's either that you might want to relate your demand model to the built environment,
Yeah.
the population, the demographics, those data you need to get. And so it cannot be purely based on this. I suspect it cannot. There has to. I'm not even sure the wait time can be observed. If it's not,
Oh, right.
has to be something else. So it's very difficult.
I mean, even like demand for taxis is a little bit like hard to pin down, right? Because like you get, I mean, I've been in New York City and various other large cities. Like, I might grab a taxi on the way to walking to the train station, like if there's a taxi available, right? Like,
Mhm.
or I might just be willing to walk to my final destination as well.
Mhm.
Like, it's all about the convenience of the taxi that might arise or not.
Yeah, so if you want for full-fledged, probably some kind of more choice involved. Yeah.
So any other questions? Okay, let's thank Professor Gall again. Thank you very much. So can you answer?
Much, yeah.
Yeah. Good. And then we're going to UTC.
I need a ride though.
Yeah, you need a ride. No, I have. Okay.
Oh.
All of us.
I'm carpooling with somebody else. All right. It's still raining out, so. I just think it's walk, but. Oh, it's something?
Yeah. Yeah, I need to just go home and come back. That's all. My mother. My mother appeared in, so she, she made lunch for me.
Yeah.
So that's the thing. Okay, so you are going back home. Yeah, I'll come straight there. Okay, you're welcome. Yeah. Can you fit in Hong Kong? No, you are not right. I thought this was like a wash. No, it's not raining.
I haven't.
It's not raining. I don't know. It's probably not a good day to walk, but if it's not raining, then
It's not raining.
pretty good.
10 minutes ago, I thought it was next Tuesday.
Yeah, have a quick.
I don't know Tuesday. And then
Naturally, today is Chinese New Year, right? We should all relax and take a break.